let's spend a second in talking about RMTS so we all have some better idea what we actually do. And we're located in Romeo, Illinois. Been in business about 7 years now. And as you all know me, I'm from Chicago Oil Company for many, many years and started RMTS about 7 years ago. We have 40 employees, 25,000 square foot facility, complete roll forming tryout facility that we can actually take shapes from the invention actually to the final shape, test it, ship the part to you, that type of thing. 6 CNC turning centers, about 75 years of experience with my engineering, myself and the rest of the guys in roll forming and tube and pipe. Finite element analysis is something new that's just been brought in the industry about 10 years ago. We can actually, on the computer, simulate what the roll form shape is going to look like and or what the tube and pipe roll is going to look like. We do a publication, which is the only one in North America that travels throughout the world. Excuse me. Also, home of Super Roll, and we'll talk about that in a second. Specialized CD trainings for the tube and pipe and roll forming business industry that actually explains how to run your tube mills, how to set them up, roll rooms. We'll talk about that in just a second. We have access to 20 years of my personal technical library that I've had for many, many years on any question that might come up, and that's always available. Okay, the tube and pipe industry is, as you know, starting to grow up just a little bit. A lot of things have been changing. This slide just actually depicts that we can actually take the whole RMTS, take it to a foreign country, which we have done, and started a roll facility to actually do your own tube and pipe mill rolls. And we've done several of those so far. The actual reason we started the company was because of Super Roll. Super Roll means that we've created a roll that actually will last longer than any roll out there relative to the D2 high carbonate chrome. We have eliminated the bore wear, the face wear, most of the time the shaft wear, reduced the regrinding cost. Per foot, it should be cheaper to run your tubing and your pipe and your roll forming based on this tooling, and that's the reason why we actually went into this business. The Super Roll is a proprietary material of D2 high carbonate chrome that we have from one of our suppliers in Germany, and that's probably the finest material that you can buy. Our proprietary heat treat is done in such a way, we've got the heat treater together along with the steel supplier, and we've come up with the right analysis to make the D2 high carbon, high chrome longevity longer than anything else. There's absolutely no grinding of the roll. As you can see, everything is done by CNC turning centers. The last thing that we do is we EDM the key, because the key has been the major problem for years, and that's what started the roll face wear, the roll wear, and the shafts, and that type of stuff. Of course, we've done a lot of split and bolted technology, and all this is new technology for the tube and pipe business, and that's what we call Super Roll. As you can see in this slide, we have a complete facility for roll forming, for tryout. We can actually design a piece, take it to the roll former, run it, send you the piece, and at that point you'll be able to put that piece on your tube mill, or put those rolls on your tube mill, and run that piece immediately without waiting to have trials and that type of stuff. We have 2 of those roll formers in our plant at this present time. And we have one that's up to 12 stands. We have one that does 36 stands. So we're pretty versatile. We can pre-notch, post-notch, that type of stuff. So it's running pretty good. The next slide is the RMTS pipeline. RMTS pipeline is a new, brand new publication that's been going on now for almost 2 years, and it's expanded tremendously. And that is just for us tube and pipe people. And most of the time it's 12 pages. It comes out every quarter. And it explains what's happening in the industry and talks about different innovations and who's doing what. And it's a good publication just for us tube and pipe guys. And like I say, it's one of the best ones out there, and it's the only publication for the tube and pipe mill people. We also have a tube and pipe PDA, the only one in the country in this world that we know of. And this is actually a PDA that does all the calculations for strip width, tube weights, horsepower, squares around, pipe sizes, coil weights, gauge to inches. It actually calculates the high frequency kilowatts that you have in your tube mill to determine the speeds that you can run, or it will calculate the speed to the kilowatts that you have in your company. So it's a quite unique little device. Nobody else has one, especially built for the tube and pipe industry. They certainly are available, excuse me. This slide just shows we have many, many, many testimonials from our customers explaining why they went to RMTS and what it has done for them for over the years. We're the new guys on the block. The finite element analysis is something we spent a minute with already, and that is just an engineering computer, very, very technical, that actually takes a shape, runs it through the tube mill, simulates it, shows us where the hard spots are or the soft spots are, and for roll forming, it's a tremendous asset for all of us. There's only a couple of us in North America that have it. We happen to be one of them. And what our focus was to the tube, the pipe, and the roll forming was to be able to go in, design these set of rolls, and have it in your plant run first time, every time. And we all know what a problem with that is when it comes to in the roll form. And this finite element analysis will take the piece of strip and divide it into a million little different dots, and as it runs through our simulation, we can tell whether it's getting hard and soft or whatever you want. We also manufacture the strip accumulator rolls, and most of us have strip accumulators, and those are big pinch rolls that go in front of it that actually feed the strip. They wear out quite considerably. Along with that, we also do the straightening rolls for most of your straighteners. We manufacture a special apparatus to check the tube mill weld box along with the fin passes, and those gauges are made also by us. This is a new piece of equipment that you haven't seen before. This is called Welds. This is Welder Enhancement Linear Device System. There's no other one like this one. This has just been invented by myself, and it's only been out a short period of time. It actually allows you now to simulate the weld at the weld box relative to the fin pass, and it has gauges on it, and it keeps it level, because we all know the most important part of high frequency welding is to make sure that the distance from the fin pass to the base and the distance from the weld roll to the base is identical. This just shows you a little bit what it looks like. If you'll notice on the bottom one, it shows you the piece of pipe that actually goes through the fin pass, through the weld rolls, and also through the, as we would call these, the lead rolls. And there's a little a sight gauge there that has tells you whether the pipe is level or not, which is very, very important. We'll cover that some more on the high frequency program today. Again, this is brand new. We have it at several customers right now that are doing just a great job. If you have trouble with your welding splits, which we all know you do, this is one of the ways to cut that back tremendously. We also make what we call an EPU weld position stand. This EPU stand is actually a seam guide that actually revolves instead of moving the tube back and forth. It actually acts like a fin pass, and it sits right in front of the weld box. As you can see, this weld box has a 2-roll weld box, which is quite different from everybody out there that has the 3 rolls and everything else. This is the weld box you should be using, as we'll cover today, in the weld box as far as mechanicals are concerned. But this is a brand new item also. But the seam guide is the key here, and as you can see, this slide shows on the right-hand side shows the EPU stand, which is edge presentation unit. And again, I'll spend another second on it because it's very important that it actually is covered with a fin pass just like the one before that, and it turns the tube on a circular motion or holds it dead straight at all times. And if you don't have a seam guide, you need to get one, but that's just one of the products. We'll cover that today also. The CD training program, as you can see, we'll be seeing one today. There's actually 8 other ones, and the first one's identification and purpose of every stand on your mill. This is for a guy who's never seen a tube mill before, and he wants to find out what makes it tick relative to the nomenclature, the terminology, and anything that goes along with it. This is a great first one for the guy.
So what happens is that as the lighter walls go through the tube mill, especially in the cluster, it kind of tends to want to go back and forth. Look at that number 1 stand over there. Yeah. With that, I had to modify it. But we're going to go in the training room in a couple of minutes, and we'll be able to answer some more questions. And let me start out by saying I'm Joe Olson. I started with the company about 20 years ago in the tube and pipe mill industry, and I started out as a bundler, and then I went into being a cutoff operator, a welder, setup man, Oh, I think my operator was probably my most experienced thing. At that point, I went into foreman, general foreman, night superintendent, and I got lucky because they had 5 or 6 different style of tube mills, and I was able to kind of pick up really what was going on as far as tube and pipe is concerned. So I had some real hands-on experience. I think the thing that really kind of hurt me the most is that I knew how to manufacture the tubing, but I really wasn't sure why. And that was really the missing key with me. So I was always on the lookout for, why, how come I should do that. And I think what happened was the people that were teaching me were learning from other people. And they had some good habits and they had some bad habits. I was fortunate enough to leave there and go to a company that was an engineering company basically specializing in tube and pipe mill rolls and engineering and helping people get their tube mills running. As a sales engineer, again, I wasn't an engineer. I'm a high school grad. And my experience strictly is from tube and pipe. But when I worked with them, I had the opportunity to go to different plants. And I went to different plants. They taught me some things. I seen different type of tube mills, big ones, little ones, ID flash cutting, rolling, die sets, jaws, blades, rolls, you name it. I got involved in it. So I got real lucky and a little different than you guys, because I'm sure you guys have been in the tube and pipe of running the mill, but you missed the other part of it, which was why, how come, what makes it work. And that's what I've got. So I think that mix, and also with being with the other people and understanding what's really going on, makes me qualified for, I think, the tube mill operator. To get the thing going pretty good, we'll start out, as we talked about today, with the identification and purpose of each stand on your tube mill. And again, we talked about it, but we're going to go from stand to stand to stand. We're going to talk about it from basically what really happens and how each stand's supposed to function and what it's supposed to do. Now remember that I'm not going to get in deeply to this with you, is because the succession tapes, tooling, setup and operation of your setups as far as actually step by step, that's later on. So the focus of the tape today is to let you understand each individual stand, what it does, and for the people that know, good, I'll reinforce it for you. For the people that have never seen a tube mill before, you're going to have fun watching these tapes. Some of the problems in manufacturing any tape or talking with many tube mill operators is that there's so many different types of tube mills. So take a second here, pick out the one that you've got. And the 2 tube mills we're going to talk about today will probably take in all of these stands because they all have a little bit different type of forming section. We're going to talk about the cluster stands today, which is side roll, side roll, side roll, and then we're going to talk about side roll, vertical, and that should cover anybody's tube mill on this. So we may use some terms that may confuse you just a little bit because you've got one of these tube mills that we don't know about, but you got a question, we'll certainly be able to answer it for you. Okay, terminology-wise, so we all get off on the same foot here. There are three things we got to understand. Is this whole tube mill here is divided into roughly 3 sections. This is the forming section, this is the welding section, and this is the sizing section. Now naturally this down here is a side view of it, and this being a top view of it. Now that's broken down, and no matter what tube mill you have, it's all called forming section, welding section, and sizing section.
The second one is setup techniques and procedures. We actually went out to a tube mill and we shot a complete changeover from start to finish. We'll talk through it, explain to you guys how to set it up, what to do and what you can't do physically online in a tube mill. Both these programs run about an hour and a half to hour and 3/4 each.
See our friends are back. You guys remember from last time, the first video program that we produced was on the actual talking and actual showing of the operators operating a tube mill relative to some of the slides. And what we tried to do at that point was to identify with them each individual stand, what each stand was supposed to do for the novice operator or even for the operator that's been around for a long time. So what we did there was reinforce some of the things that he should have known that I'm sure that he knows now. And Mark and Bob were this last time, if you remember, we were at the tube mill, and as we go through this program today, we're going to go back to that tube mill, and we're going to pick up a couple of points that we think are important from slide number 5 to maybe slide 15 to 20 or whatever it's going to be, and explain to you live on how to set this particular tube mill up. If you'll notice, the first program that we've talked already has been identification and purpose of every stand on your mill. Now, we spent an hour and a half talking about that, and as we go through the program, we're going to reinforce it just a little bit by picking up some of the major points I think we should put together so the guy can always kind of know what he's heard. I'll reinforce it again. We'll go to the tube mill, reinforce it one more time, and he can watch the tape as many times as he wants to. The process of it, as you can see, is now, today we're going to talk about the actual setup techniques and the procedures. And with that, we're going to get down into down and dirty and talk about why the tube mill runs, what it's supposed to do, and how it's supposed to react to every situation that I think you guys can possibly have.
Excuse me, Joe, I was watching tapes 1 and 2, and I was wondering, is there going to be a tape where you're going to deal with high frequency and electrode welding in greater detail?
What's happening here is we tried to break the programs up into the setup techniques and procedures would be strictly mechanical. I do cover some welding, but not a lot. So the welding part of this program will be under comparison of tube welding processes. And when we do that, we try to do what we can to spend a lot of time on radio frequency, that's most predominant, and also on low frequency. The TIG welding part is in TIG welding, and there is some laser welding in the number 6 program also. Okay? So each one of them is custom made for that particular program and those particular people. So that's where we're at today. So let's move on a little bit. Now, for the people that have saw the first tape, this is exactly where we laid off at. Okay, and that was now we understand what the tube mill is, how it works, and what it's supposed to do. Now we got determining on what happens when we start the tube mill up. Well, I can tell you what happens most of the time. Most of the time, we have a problem. If we have that problem, we got to be able to understand where the problem came from. So if we isolate the problem by saying the first one could be, let's make an example. We have a weld problem. Is the weld problem a steel problem, a width problem, or a gauge problem? From an operator standpoint, he doesn't know. Do we have a tube mill problem? If he hasn't checked his tube mill, he doesn't know. Does he have a tooling problem? If he didn't check his tooling, he doesn't know. Does he have a setup or an operator problem? Of course, that's him, and he's never got a problem with him. Okay? And that's understandable because I was an operator before. I never had a problem with me either. Okay? So what we're going to show you today is how to eliminate and isolate the problems before you get them. And here's what that means in summary. The first thing we'll do is we'll talk about how to check the steel, the width, and the gauge. Okay? And as an operator, you're not concerned with the physicals or the chemicals. You're only concerned with is it this wide and is it this thick? After you've done that, you've done your job. So at least when you run the tube mill, you know that you're going through that, and as you're going through that, you know that, hey, got the right width, got the right gauge. How do I know? Because he told me so. And that's all as an operator you've got to know. As far as the tube mill is concerned, we'll spend 10, 15 minutes inspecting that. Not a lot of time because changeover means money. So at least you got an idea. If one of the passes are off, you can shim it and fix it right there. Write it down, write a note, and say, hey, next time I run this size, this roll's bad. We got to get it fixed. As far as tooling is concerned, okay, you should have somebody checking your tooling, or you check it yourself, and I'll show you how to do that today. So now, you run into a welding problem, or you run into a straightening problem, or you ran into some kind of a problem, you say to yourself, okay, can it be steel width and gauge? No, I checked that. Can it be the tube mill? No, I checked that. Or I did find out what the problem was, and I'm not using that pass. Type an example. Is the tooling okay? Yes, I checked that. There's only one thing that's called setup and operator. That means go back to your setup chart, recheck it again, recheck it again, and recheck it again until you get it right, because you're so close. If you're back to the setup of the operator, you know what you got with the setup chart, you're close. You know what's going on. And we'll show you how to find out after you got something wrong. You say, well, okay, now I found out it's wrong. What do I do? And we'll show you what you can do later on to fix that problem on the tube mill. Make a note, send it back to the tool room. If you don't have a tool room, put it in the box, take it back to us. We'll make sure it's in the center for you, and we'll fix it for you. Worn or chipped corners, of course, we're looking at the radiuses now. They can be inspected, and you can inspect them a lot of ways. We normally make gauges for you with your tube mills if you like them, and the gauge would sit in the tube mill, and you would see how the radius looks like to find out how bad or how good that is. Okay? You can check the root diameter, but normally the root diameter is the dimension between here and here, but normally it will not stop you from running. This problem will hurt you, this problem will hurt you, and also this problem here, the radius being blown at the last sizing pass, will hurt you. Okay? Okay, so you don't spend too much more time on it, but that's where it's at. Somebody's got to check that tooling before it goes down to the tube mill. And you can see why. I got a welding problem. I got a straightening problem. I got an OD problem. What do I do? Which handle do I turn? Is the tube mill backline off? Was that roll worn to the point where I can't fix it? Where I can't make tube for it? Okay. What other problem can I have? Maybe I got it set up wrong. You can't, as a tube mill operator, look at all those problems and put them in your head and say, which one do I start with first? Because you get so confused by saying, I checked that one roll, that roll's okay. Did I check the tube mill, that part was okay. Did I check the tooling, what, did I check that piece? No, I'm sure I didn't check that piece. And all we do is, as we've done for years, is keep on turning the handles until we get lucky. We always get lucky, the tube mill always runs. We always get lucky, okay? So no more getting lucky. Check the tooling, have it checked. These are some of the parts I've told you. I didn't show you where you had to check the breakdowns. I didn't say to go in and put them on comparatives. I didn't say anything like that. Get some idea where you're at, then we can work around it. Okay. The problem, as we just spoke of, you can just talk a minute for you. You can see what happens when one of the spacers, if you fix your own, of course, you don't put the chamfer in there. What happens is that doesn't go up against the shaft. And now the whole spacer, whether it was good or not, brings the whole center line of that mill out 5, 10, 15 thousandths, and we might as well just forget about what we started from. Okay? Moral of the story, if you're going to do your own spacers and you chop them off, make sure you put a chamfer on them. Taking the rolls off. Okay? Now, stay with me now. First part of the program is completed. We inspected the tooling. Okay? We know what we got. Okay? So the next thing we got to do is take the rolls off. A good portion of the time, the rolls will get stuck on if you run them any length of time. And in this day and age, it doesn't happen too much too ever. So what we do is we put a gear puller on it, take the roll off, make sure you fix up the shaft, and replace it if you have to. If you don't have time, clean it up just a little bit. So we won't spend a lot of time on that.
Am I going to damage the roll when I heat that up?
Yeah, sometimes if you just keep the heat going around it, you may soften a little bit, but maybe a half a point or a point. But most of the time you don't turn it red, of course. We're looking to heat the roll so the heat expands. And when it expands off the roll, you can take it off. So works out pretty good. Now, this is mill inspection. We're going to spend some time on talking on mill inspection, and we're not saying we're going to rebuild the mill. We're not doing that. We're not saying we're going to change shafts. We're not saying we're changing nothing. The first thing we're going to determine is what is the tube mill shape of when I put this nice set of rolls on that I just inspected. That's all we're going to do. You will decide what you're going to fix and what you're going to do from that standpoint. I can't tell you that. But I can tell you some of the easier things to fix. If some of the back lines are off or something's wrong, I can put a shim on, you can fix that. I'm not advocating that we stop, change over the whole mill, strip it to the base, reshoot it. None of that doesn't make any sense to me. Okay? What I'm trying to do is make sure as an operator you identify what's wrong with that tube mill so you can get around it. Let's assume number 3 pass is bad. It's got a bad shaft alignment. We can either put a shim on it or don't bring it down so tight. And back away from it if you have to. So the mill inspection is a major importance. Usually mill inspection starts off to be the first thing that's important to us is the shafts. So the first thing we're going to do is we're going to visually look at the shafts and feel them. If they're all in pretty good shape, we don't need to measure them. One that's got a little bump on it, you may want to measure it. Normal tolerance on the shaft with us is really close, like within a half a thousand or so. Okay, the tolerance on the roll bore sometimes it gets out is 4,000, but I'll make the roll half a thousand larger. We'll make the shaft a half a thousand under. We got a thousand between getting on and off. Okay, that's how tight that fix is. It has to be that tight to make sure that it doesn't hurt the roll or ruin the roll.
Number 3 is tooling design and considerations for the average tube mill operator or even the person that you have in charge of your roll shop, if that's what you have. It explains to him exactly what we do. We don't get into too much depth relative to the design criteria, but I tell him the things that I think he should know relative to modified edge form, W form, fin passes, that type of stuff. It's a great little program.
Is which and how it works and how it's supposed to work. We've talked about the actual setup and procedures and the techniques, showing you actually what happens when you do have to set up a tube mill, the things that we would normally do to set up a tube mill and from an operator standpoint. I think what's important for you is that after you learn
and understand what we've talked about for the last two programs, the tooling plays a major part. You can have a great tube mill, and you can inspect the tooling and and stuff like that. If you're not aware of what really the tooling is or how it's supposed to perform, and I really think you're kind of lost. I think every one of us as tube mill operators should have at least a working knowledge of really what's happening when it comes down to tooling. So, as you can see by the slide, we're going to talk about setup techniques and procedures. That's what we talked about last time. This time we're going to talk about tooling design and considerations. Again, everything's going to be basic. We're not going to get too far out of line for you. We're going to show you what edge forming is, what modified edge forming is, and all the things we think you should know about relative to tapered fins and straight fins and different types of weld rolls and different types of materials. We're going to talk about some new designs you haven't heard about before, like cage forming. We're going to talk about some new designs, what's called split and bolted type designs. Those are strictly information for you. What you'll see today is some more information relative to the tooling design, and we won't get, again, in too depth, so just sit back, relax. We're going to talk about the real basics of the tooling.
Problem number 4, making squares from tubes and rounds. This is a unique program that you would want to have because it explains all the ins and outs from making squares out of rounds, and there's some technology involved relative to corner radiuses, straightening of the tube, marking, diamond shape, flat shape, that type of stuff. So that's a really important one.
I see our friends have joined us again. Welcome in. We're on our number fourth tape here. First tape we've talked about, of course, has been the actual speaking of the tube mill, how it works, what it's supposed to do. The second one was the actual setup and procedures. I'm sure you have that one. And that was reinforcing some of the operator training type situations. The third one was familiarity with the operator relative to its tooling. And the fourth one is going to be some squares to rectangles from round tubing. As we go through the program, you're going to find out some things that you really didn't think were true that are true, and some things that you thought were untrue are true. That just means that back 30, 40 years ago when we were making wire naturally was always round. So to take the wire from round to a different shape, all they did was make a square orifice of some type, die, grab the wire after it came through, grab it by the hook, pull it all the way through. When they did that, they pulled that round wire into square. When the first tube mills were built, I made a round tube, did a pretty good job of making a round tube, and somebody decided, well, we can make this square tube. So in order to make the square tube, they figured they'd take the wire scenario, okay, instead of pulling it through, they'd push it through. So they made what we call Turk's head today, four rolls, put Turk's head, and they ran the tube through it, and man, it came out great, it made a nice square. No problem. Naturally, what happened at that point is once that caught on, somebody wanted to make a same size square, but a little heavier tube, heavy gauge. So they did that, and they got to a point where they started pushing it through. It wouldn't go through because there was just too much cross-sectional area being taken place, and the gauge was too heavy. And my contention is that at that point there wasn't such a gauge problem as it was a mother tube reduction problem, as we'll discuss today. So instead of them putting on another Turk's head, they felt it was a little cheaper just to go ahead and put something in the sizing mill to break it down a little bit to propel it. And that's really how everything started, and that's why most of us today have sizing rolls in our sizing. That's why we have squaring rolls in our sizing with a multitude of shapes, which I think is a mistake. Number one, it's difficult for the operators. Number two, it sets up many roll marks. The rolls are expensive. They wear out quickly. You can only run it in one particular type of formation, flat, diamond, or offset. And that their mistake was, instead of going out and spend some money on another Turk's head, they kept on backing up into the sizing, and today we've just got millions of problems. A good portion of my customers now will round to square based on a good understanding of what the mother tube should be. And we talk about Turk's heads, squaring Turk's heads, we normally talk about reshaping and squaring Turk's heads. It didn't say re-reduction, it said reshaping. So if you understand where the mother tube is at, meaning that the size that you need to go into that square and just reshape it, it's not a difficult procedure. If you try to use the same mother tube for all the multiple gauges, of course, the heavier gauges becomes the square of the corner comes up. What happens at that point is you tend to force it in there, you take cross-sectional area reduction, it starts backing up, and you start having problems with roll marks and a lot of roll wear. So I'm going to explain to you, excuse me again, I explained to you the program today relative to different ways of doing it, what you're doing today, what you should be doing, in my personal opinion, and how we think the end result should be. So, if you're all ready, we're all ready. We'll go to the first slide, and we'll talk about just some different ways of making this square tube from round, and there's a bunch of them. And the first one, of course, is a hot process, and we're not going to spend too much time on that one. Extrusion, copper, and aluminum, that means you just take this big billet and they force it through an extrusion mill, which doesn't make us a lot of production, but there's still a process for it. Seamless, hot finished. Welded tube, hot stretched. Draw bench, hot and cold. Form square, weld square, and weld round and reshaping inline. The bottom two are the ones we're probably going to spend some time talking on because they're the most universal. And they're the most ones that are normally run on a tube mill today. So the first one, form square, weld square, just to summarize for you, is a series of shaping rolls in a tube mill that you can run most of your shapes on the same set of rolls by interchanging rolls back and forth, and we'll cover that one today. Now that's good, but then it's got some bad. The bad is you can't make any rounds. Okay, so we lost some flexibility there, but if you're in that type of market, then that's what you want to do. The second one, which is weld round and reshaping in line, is the one we're going to spend most of the time on because that's what everybody uses today. From a round into a square, from a round into a rectangle, different corner races, sharp corner races, diamond shape, flat offset. That'll be the discussion for today.
Number 5 is TIG welding, tungsten inert gas, and that is for the stainless steel people. It covers the whole program from roll design to gas that you use relative to speeds and that type of stuff. So that's a great program also.
Good. Okay, looks like we finished up the round and square program, which was number 4, I believe. Right? Yeah, number 4. And we did some interesting shooting again out at National Metalware. This program here is basically for what we call stainless steel welding. I'm not talking about the 400 series as much as I'm talking about the 300 series. The 300 series, as we know today, is a non-magnetic material. So it's got to be welded in a certain way. Some of the newer technologies that we have today are actually welding the 300 stainlesses with radio frequency welding. The scope of the program today is not to get in too deeply on that as far as welding is concerned because it's covered on number 6. But from an operator training standpoint, we're going to talk about the basics of stainless steel welding by use of TIG, tungsten inert gas, and we're not going to get too detailed in gases and other things that must happen, but stay more or less mechanical. I want to talk to you about a little bit of roll design because that's really important here. And the roll design on TIG is not covered that much in the tooling design consideration because I left it strictly for this program. But you can have all the gases you want, do all the welding you want. If the roll design is not correct, there's a major problem because, number one, there's no lubrication for this tube mill. You can't have any lubrications at all, and we'll talk about why that is. So from an operator standpoint, we'll cover the TIG, we'll talk about the stainlesses, excuse me, we'll discuss the weld box, we'll discuss about how the gases are entered into the tube, we'll talk about some other things. But mainly we'll spend a little time on the design of the tooling because I think it's important for you guys to know what has to be done, how it flows through the tube mill, that type of stuff. So, you ready? I'm ready. We'll get started and see what we got coming up here. Now, first of all, we talked about a cast weld. Again, that means that what casting normally is casting means you take this big bowl and you fill it up with metal and let it cool off, and now it becomes a solid piece. There's all kinds of castings around, okay? Primarily, that's what we're talking about. We're going to take this piece of tube, run it longitudinally, we're going to melt the material, and then we're going to hold it until it gets nice and hard. Then we're going to take off the pressure and continue a piece of tube. You can only do that at a certain speed relative to the amount of heat you put into it and how long it'll hold that piece of material. So when they say about the cast, that's what they mean. We're going to heat top and bottom. We're going to supply gas on the outside and the inside. The outside mainly for contaminants. The inside to support the weld. That pressure and that type of gas will keep that weld up so it doesn't drip down and give us drippings, that type of stuff, which could be possible. So there's a lot of support there. And then for the operators, if you'll notice, inside there's a couple rubbers. And the rubbers, the tube runs through the rubber and fills up the little chamber while the tube's running past us and keeps everything, making a nice cast weld. So that's what cast weld's all about. Now, strips edges are heated to molten, and they hold until the molten puddle is solidified, which I just kind of said. I read that slide for you a little bit to make sure you read along with me, because I want you to understand that that's how that works. I'm sure most of you are already making the TIG welding already, and that's good. You should be doing that. But you should know why, how come, and it'll make a better operator out of you. Okay, so inner gas or gas mix is used to prevent atmospheric contamination, as we talked about, some types of oxidation, that type of stuff. It allows clean homogeneous weld, argon outside, hydrogen inside.
Number 6 is comparison of two welding processes. I actually went through all the two welding processes, put them together and explained each individual one, from TIG welding, high frequency, low frequency, laser, that type of stuff. And it shows you what application you need for this type of welding.
Number 6 video. And the number 6 video, of course, will cover, basically for operators only, the tube mill operating techniques of high frequency, low frequency, a little bit of laser, and a little bit of TIG. For all my new friends that just joined us, I'm sure you've seen the other 5 tapes, at least I hope you have, because each one of them dealt with something particular like this one will. And this one particularly deals with the frequency and the low frequencies and some of the other weldings. Now let's understand that if there's any engineers in the room that are electrical engineers, that type of stuff, I'm probably going to bore you, because it's for, again, this program is for operators only. So operators only mean that the guys are actually on the tube mill and want to know about the coil. They want to know about the impeder. They want to know about the welder, the high frequency welder. They don't care if it's 450,000 kilocycles or it's 450 million. It doesn't make any difference to them. So we don't spend a lot of time on that. If you need to know electrical, you need to know something like that, I suggest you talk to your frequency people that understand it more than what we do. We're operating people, and we're here to train the operators. So we're going to skip some of that stuff only because I don't think it involves them. And we're going to be here for 45 minutes to an hour, so we want to talk about basically the mechanics, how they work, and how they're supposed to work. Okay, my boys from National Metalware are back again. We welcome them, and they're going to ask us some interesting questions today too. So let's go to the next slide, see what we got. And for some of you that might have just bought number 6 program, which I seriously doubt, again, this is the one we're on, comparison of tube welding processes. Okay? And again, the comparison means that we will address all the welding processes, but talk basically about radio frequency and low frequency, because that's what dominates the market, about 99% as we understand it. I think the things that worries me the most is that everybody feels that I got a brand new high frequency welder and I got a brand new low frequency welder, and all I'm going to do is put it on my tube mill, and boy, is it going to do a nice job for me. Well, that's not true. Think of the high frequency welder, in my opinion, as a piece of welding current that you plug into the wall, it turns on and puts current to the coil, and then forget about it. Okay, just forget about it, because it's not going to do anything special for you. It's not going to help you. There are no techniques that I know of that are going to make that welder do things better for you, with the exception of roll design, presentation to the weld area, where the impeder is going to be at, and we're going to talk about that today. So forget about which way the current runs, up, down, backwards, whatever, and spend more time thinking about what the mechanical parts of the mill are. The radio frequency welder is a high frequency type welder. The low frequency welder, of course, is alternating current, and it presents the weld current a little bit differently, which we'll discuss today, but We don't need to know exactly how it works, just primarily how it works for the operators. The slide we're looking at now is a primarily slide, and I want to get you familiar with on the tooling. If you didn't get the tooling program, if you did get the tooling program, I still want to cover this for you. What radio frequency, low frequency, any type of frequency welding you're going to run is most important is the presentation of that piece of tube to that weld area so it can process the current into that tube. If the tube is not presented correctly, I don't care what kind of current you put into it, the weld quality is going to be less than adequate. So we got to be careful and understand that the thing is most important is the presentation to the weld area.
Number 7 is managing your own roll room. We spent some time in talking about how to check your own rolls, make sure they're in the shape they should be in, how to put them in certain categories, and what actually needs to be done in your roll room.
I'm Mark Grant, sales engineer. I've spent the last 20 years being either an operator, supervisor, or a sales engineer in the tube and pipe industry. Today we're going to present to you the 7th in our series of tube mill operator video training. This one here today is going to deal with setting up a tool room in your plant. We're going to help you set up a tooling inspection department within your plant so that you will be able to develop a system to improve your efficiency of operations as well as track and maintain your tooling in-house. Measuring success one roll at a time. That's our goal here. We want to establish a quality program for inspecting your roll tooling. I read a book about 20 years ago by Robert Townsend called Up the Organization. And in that he had this quote: if you don't do it excellently, don't do it at all. Because if it's not excellent, it won't be profitable and it won't be fun. And if you're not in business for fun or profit, then what the hell are you doing here? And that phrase has stuck with me over the years. You see, all of us enjoy our job, or at least most of us do, but all of us are here to make money. And so our goal today is to help you become the most profitable company you can. And I think when you look at it from a profitability standpoint, the answers come a little bit easier. Consider to yourself, what is an expensive part, and how would you prioritize them? I'll give you my list of 6. The main objective here is to determine what we're going to do with the tooling. Are we going to send it out for regrind and reconditioning, or are we going to say this tooling is acceptable for the next run of production? That's all we want to do. We're not concerned about the engineering designs, only the functionality of the rolls. I like to approach the situation first by doing a visual inspection of the tooling, looking for the obvious blemishes and problems that might occur. Then after the visual inspection, then I'll go into checking the bores and the faces, and once I've done that, then I'll go directly into checking the contours of the rolls. Now on these here, there's 2 ways that we talked about. One, we could use a template, and on this particular roll, we could come in with a template and lay that in there to check that. Or we can just visually look for wear. Now what I'm going to do is I'm going to do a quick once-over. I'm going to look at the rolls. I'm going to feel the rolls, and I can feel down in here some grooving starting to take effect, where these rolls are starting to wear. And I'm not real pleased with that. That could be a problem with the forming, particularly since what I have here is a modified edge form roll. And it's kind of critical that I have a decent form. I'm going to look at the edges, going to check for chipping out in the root areas, chipping out on the rims. I'm going to check the rim surface. This roll here checks out okay, but I'm sure you've seen from time to time rolls in which you've got flat spots worn on here, where the rolls have actually come down and rimmed out against each other and have worn a bad spot. Overall, these rolls don't look too bad. Another thing that I can do is I can lay the top roll into there and lay the two mated pairs top to bottoms together. Now you're not going to be able to see this because of the way that I've got it sitting, but what I'm going to be looking for is how those contours made up to one another. And if it looks like it's in still pretty good shape, I'm going to let it go. If you've got wire gauges in which, okay, if your material thickness is 40 thousandths, if you've got a 40 thousandths wire, you can also run that down through the contour to check to see how much wear you've got. If you don't have precision plug gauges, or you don't want to put the money to invest in a precision plug gauge, something else that you can do, and let me move this stuff out of the way. What I have here is just a chunk of a shaft. It's an old shaft. Probably up in this area would have been where the roll had worn it. I just took a good section where the spacer was. I miter ground the two sides. I've got the keyway. If I want, I can set a key in. Clean the inside of the roll. And I can use this for a plug gauge to check my roll tooling. Coming down in on the keys. Got a nice fit. Roll sits on there nice and snug. And the key seated pretty decent. Now on the visual inspection here, when I get to the breakdown, I've got a severe problem. If you're looking at this rim out here on the edge, what I've got is I've got this roll is being just chewed up along this edge. Now on the other side, I don't have that problem. My suspicion is that I've either got a misalignment in the spacers, or I've got an operator that's cocking these rolls off to the side and it's digging in.
Number 8 is operator training for high frequency welding, which you are going to see today. Books you want to from all the major welder manufacturers, and you will get lost, and you will get lost quickly. From the standpoint of that, because I've been there and I've done that. So I try to take that all apart and give you some real basic things on really how this stuff works. If you notice this slide, there's about 15 to 20 different things that influence how you're going to make a good weld. And of course, the first one, as you can see, is the coolant, lubricant environment, and we'll talk a little bit about that today. Some of these things that are concerned, that point to high-frequency welding, we're not going to discuss, because I think it's too deep for us as far as operator is concerned. Take an example, the frequency of the current. We can talk about that all day long, but from an operator standpoint, I don't think that's important to you. The electrical power and efficiency, we're not going to talk about that. We're going to talk about some of the other things, like the distance between the induction coil and the pipe. Now we got a handle on something. Now from an operator standpoint, we need to understand what that distance is, and we're going to cover that some more today. Condition and cleanliness of strip edges, very important. We need to understand that. If we can't do anything about it, we still need to understand it, because further down in the tube mill we can make this thing better. Presence of the strip edges, as we talked about. The induction coil, the welding unit relative to the impedance we need to talk about. The V angle, we're going to talk about that. Very important V angle. Everybody says, oh my God, what's that? It's a very simple process. It's just a little bit of knowledge of understanding what the parameters are and where it could be. There's about 3 or 4 things we're going to spend some real quality time on today, understanding how to make a high frequency weld that's best we can get. Alignment of strip edges we'll talk about, continuous formation of the V, which is very important, we'll talk about that. Welding speeds and the cleanliness of the impeder. All those things we're going to talk about today, and I got it narrowed down to about 4 or 5 different things, and we'll talk about those as we go through. This is going to be a little bit fun. I'm going to go slow for you. We're going to be here an hour to an hour and a half probably, and the things we're going to talk about is the welding mechanicals. We have 2 roll boxes, 3 roll boxes, 4 roll boxes, 5 roll boxes. Which one's the best? What about the material? On and on and on. We'll speak of tooling only from the point of how it represents itself to high frequency welding. I'm not going to go into design. I'm going to tell you what I think we need the basic stuff for to make sure we get 100% quality weld. The current path is important to the operator, because he must know how the current travels from this induction coil or the inductor and into the tube itself. The impeders are important. We need to have a basic understanding of those. The work coil, of course, is the coil that goes around a tube that generates the energy that goes into the tube and pipe. We need to talk about that. Heat and temperature, which are one of the most important things for us to do. Take an example. Most of us, when we have a bad weld, the first thing we do is turn up the heat. And I'm here to tell you, and I'm sorry to tell you, that that's wrong. We don't need to do that. In some cases, I'm sure we do when the weld is too pasty or not hot enough. But that's something we need to spend some time on, which we will today. The setup certainly is important. If we don't have a good setup, the high-frequency weld is just not going to work on a continuous basis to make you sure you get 100% good weld. I'm going to talk about testing just a little bit today on destructive and non-destructive, and I'm going to do it very simply so we have some idea what it is. And we're going to spend some time with a little bit of micros. And the micros are actually an analysis of the weld after you've made the weld. That's probably under a microscope 50 times. And there are some certain things you can look for, and we're going to touch a little bit on it today. A lot of us don't do that. Some of the bigger companies do, and I think it's important. But from the operator standpoint, it's good for him to have some knowledge on really how this stuff works. We talked about the forged weld versus a cast weld. This is not in any way, shape, or form a cast weld. The material does not need to be totally molten. Matter of fact, it cannot be molten. If it is molten, what happens is that the side of the weld, which we call the haze, the heat affected zone, becomes plastic, and there is no forging pressure. So we're speaking of a forged weld. In a forged weld, as I can relate to you, in the old days, if you remember the anvil and the guy heating up a piece of material and hammering it with a hammer and then squeezing it together and holding it, that is a forged weld. Okay, this particular slide, which I think is probably one of the most important ones. I have another important one for you, but this one I think is a major importance. And we're going to see this probably 3 or 4 times today. And basically it talks about the amount of heat or temperature we need in the tube to manufacture a tube. We've talked about a little bit of forge versus cast weld. We're going to talk about the tremendous amount today. And I may say the same thing 3, 4, 5 times because I have to. Because you have to understand this is not a cast weld. It's not molten material. It is a piece of pipe that has 2 hot edges that get forged together. Take an example here. You see the 650 degrees in the first one here. The 650 degrees, which is 1200 degrees Celsius and higher, is for the haze. The haze is the heat affected zone. It doesn't do anything but just smoke or get red. So as you can see at that degrees, nothing's going to happen. You can't forge it. You can't do anything to it because it's just getting up to somewhat temperature. If I notice the second one that says 875 to 1400 C, which is Celsius, 1607 to 2642, which is degrees Fahrenheit, that is the forged temperature range. So what that means, which we'll cover, you're going to see this thing many, many times today, and you're probably going to hear the same thing that I'm saying, is that is the temperature that we can forge a piece of tube, meaning that we take the 2 edges, we heat them up, we put them together. I said heat them up. I didn't say we make them molten. I said heat them up, put some forge pressure behind them, squeeze out some impurities, and make a good weld. If you get any higher, example on the third piece shows you 1550 to 1725 Celsius. It's 2822 to 3137 degrees Fahrenheit. The metal is molten. I'm not going to tell you that you can't use that all the time. There will be some times where you can, that you may need that just a little bit based on maybe some stainlesses, based on maybe some real thick walls, 187, 250 wall, 315 wall, 350 wall. In that area, you may need to get it just a little bit molten. And not because you need to, is because of the proximity effect, and also because the edges on the top and the bottoms will probably melt off a little bit sooner than the inside that needs to get to this degrees of 2282 to 3137. So at that point you may have to get there, but on the normal stuff you won't have to get there. The last one, 1725 Celsius, 3137 Fahrenheit. As you can see here and here, that metal is also partially molten. And I say partially is because it could be 50% molten. There is no backup for it. You probably will not be able to make a good weld at that point. And number 9 is roll management data system, cost tracking per roll. What we actually do with that is we actually give you a computer program that shows you how to track your own footage per each individual roll, keeps cost of the roll, how many times it's been reground, and it puts them in sections that you'll be able to identify either roll as far as inventory is concerned, as far as how much footage is on it, how much do they pay for it, how many times it's been out for regrind, that type of situation. It's really a great program for the people that want to keep track of really what's going on with their rolls. Great roll program. Now, for you to believe everything that I've told you, I think you should have some idea, who I am. And again, I started back in Allied Tubing Conduit in 1963. It's quite a while ago. I'm sure I don't look that old, but believe me, I am. I started out as a labor bundler. I was a cutoff operator. I was still going to school at that point, and went to tube mill operator, recut person, supervisor, and also ended up as a tube mill foreman. I spent 10 years at Allied, then I went to Lamont Engineering Company, presently Turkinella Machine Company, and as a young sales engineer who didn't know too much about anything, and boy, they taught me a lot. After that, I went to Atlas Tube up in Canada as a plant manager. I worked for Mr. Zeckelman, Harry Zeckelman's father, and learned a lot at that plant. I went 5 years at that point to Tesco as a partner in Tesco's tube equipment sales company, and we were focused on selling machinery for the tube and pipe mill business, including rolls all over the world. I was vice president in charge of sales for them and also for Rollcraft, and I had 2 years at Sanyoseki. Sanyoseki was a Japanese manufacturer of tooling that wanted to come into North America. So got quite a bit of experience with that. I spent a year at Turkinella Machine Company as a sales manager. And then I started a company called Chicago Roll Company in 1985, and then sold it in 1999. So I've actually given 50 seminars domestic and 25 foreign as a guest speaker on pipe mill tooling and training all over the world. I wrote and produced the only tube and pipe mill training programs in existence, which are the volumes we've talked about this morning. I have 20 published papers that I've published throughout the world relative to tube and pipe mill training, rolls and devices, that type of stuff. I actually have 44 years in the business between engineering and sales, manufacturing. So I've picked up a lot of experience. And experience in all the styles of tube relative to pipe, roll forming, high frequency, low frequencies. I've actually went in there and done it myself. And I think the unique ability that I have is that I've been there and I've done that. I think that gives me some background so you guys understand when I explain something to you, it's coming from where I've been and what I've done.